Truckee. My name is Lidar. I'm going to lead through tonight's event. We're going to talk about smoke and how to predict it, maybe even how to prevent it. That would also be good. Before we do that, a few important things. This whole event and all that we do here is possible because we have wonderful sponsors. We have our gold sponsor, Holland & Hart, has been with us and helping us for a long time. We have Heads Up Health, Mobile Law, and Mountain Workspace as sponsors. In addition to our sponsors, we have community partners. That is the Truckee Chamber of Commerce. We have Truckee Community Foundation, the Lift Co-working, and Peace of the Hill, which is where we're meeting tonight. So we're very thankful for their sponsors. We can always need more, especially now that we are an official nonprofit that also creates a little bit of overhead. It also means that if you donate us $1 million, we can give you actually a tax deductible little paper. So that's all those good things about nonprofit, but it initially requires a little bit of extra investment. So if you want to be a sponsor, it would be wonderful. And you can find more information on our website about this. We can have also individual sponsors. Individual sponsors actually get a great deal. They get recognition and can really feel good about it. And not only that, they get free entries, plus an extra drink. And it could be a beer or wine, or if that's not for you, then you can have 2 sodas. So you get a bunch of benefits, and really the way you help us is because we know that everybody can make it to every event, but it's an annual fee, and you help us sponsor those events by doing that. We're very thankful for that. Tonight, we are talking about why we in the Tahoe region get so much wildfire smoke. How can we predict it? Some of the great, weird phenomena that happen when it gets really hot. And our speaker today is Dr. Neil Lareau, and he's a physicist, which is exciting to me because it was one of the 2 things I was considering studying. Ended up studying engineering and then going to business. His specialty is the atmospheric sciences. He also did a dissertation about that, and he's now teaching in this area at UNR as a professor. And it's interesting. This year I was traveling, like last time when we had I was away. And I get those alerts, red flag warning. And I'm always nervous. This year I was particularly nervous. I'm going to go home and find only ashes, or what's going to happen? And especially in years like this when it's been dry forever. I'm so glad that it rained last week. So there's something going on here that makes us a bit nervous about the weather situation. So we're going to learn more to understand it tonight. And as I said, if there is some additional inspiration on maybe how to prevent the worst, I'm also looking forward to learning about that. So thank you for being here.
Sure. Great. Thanks for having me. Do I use this mic or just this mic? Okay, great. Oh, there we go. All right, thanks. So yeah, my name is Neil, assistant professor at UNR, but I've only been there for a little while. Before that, I was down at San Jose State University in the Bay Area, and so no stranger to the fire conditions that we get here in California. I also feel like, based on that picture, I should kind of like cock my head over here while I'm talking. All right, so yeah, I spend my days thinking about fire and thinking about weather and thinking about smoke. And I'll come back to this title a little later in the talk, but my goal as a scientist is kind of to advance our understanding of something we call fire-atmosphere interactions. So how wildfires interact with the overlying atmosphere and the range of possibilities that we get from that. And I'm always supposed to acknowledge my funding sources. So some of this work is sponsored by the National Science Foundation. And I also used to work for a group called the Fire Weather Research Laboratory at San Jose State and now at University of Nevada, Reno. And hopefully these pictures give you a little bit of a feel for the sort of things that I'm going to be talking about today in terms of these kind of explosive wildfire conditions that we can get here in the western United States. Okay, so kind of the tagline for tonight was proposed based on this last summer and how much smoke we got here day after day, especially from late July into mid-August or so. And so the pressing question is kind of, why does Tahoe get so much smoke? And of course, Bob Dylan answered that a long time ago for all of us. But really, it's all about where the smoke originates and where the wind is going to take it. Although there are a lot of complexities in that equation when you really dig into it. But this is a great satellite shot, or maybe not so great, depending on your perspective. Probably from, I think it was maybe the last few days of July this year, and we can see some of the major fires burning in California. This went on to become the biggest fire in state history. This is the Ranch Fire, the Carr Fire up in Redding, the River Fire. I think this might have been the maybe that's the Ferguson Fire, and maybe the Donnell Fire or something down here. In any case, lots of fires, plenty to choose from. Where are we? We are right there. This is a rare moment this summer where we were actually between these smoke plumes. So, yeah, we could actually see the lake on this day. That must have been a good day. Okay, so the answer to this question is really quite simple as far as why do we get so much smoke here. Part one is lots of fire. And this is just a snapshot from the end of the season this year, or maybe just a couple weeks ago, of all the fires that occurred in California that were managed by Cal Fire. And so this doesn't even include the fires on federal land like the National Forests and National Park Service. And we can see just we have plenty of sources of smoke in your typical summer in California, and this was even a atypical summer in terms of the number and acreage burned. And so when you have a huge distribution of fires like this, well, it doesn't really matter where the wind is blowing from. It could be blowing from any direction on any given day, and the odds are that we're going to get some smoke coming in from somewhere during the peak of fire season, which is about July 15th, right up through about now. And yeah, fortunately we got some rain, breathe a little sigh of relief, and the mountain biking's better, so that's cool too. All right, so that's kind of part one. Part two is there's a local mountain wind system that develops here in the Tahoe Basin and over into the lee side of the Sierra Nevada called the Washoe Zephyr. Has anybody heard of the Washoe Zephyr before? We got like one yes. Okay, sweet. So the Washoe Zephyr is what we call a thermally driven wind system, meaning it depends on the heating of the atmosphere, just the daytime heating. And the way this works is that around midday, the mountain slopes, so this is a kind of a cross-section across the Sierra Nevada, so down in Sacramento, up to the Tahoe Basin, and then down into the lee side over here. So during the day, it gets quite hot along the mountain slopes, and that has the effect of drawing in air from lower elevations, and we get these kind of upslope, up-valley winds that develop every afternoon. And so that's a pretty common phenomenon. What's a little bit less common with the Washoe Zephyr is that it gets so hot in Nevada that instead of the winds just converging up to the mountain slopes, that wind keeps going, and by late afternoon, actually crosses the crest of the mountains and brings any air that was over here and any pollution that was in that air up and across the mountain range and all the way over into Nevada. And so it's kind of an atypical wind in that the winds actually end up blowing down the lee side, even though they're driven by heating. Typically, we think about heating as drawing air up the slopes. And there was a rather spectacular video illustration of this flow associated with the King Fire a few years ago. This is back in 2014. See if I can get this to run. And so we have a big fire burning on the western slopes of the Sierra here, and we can see this big smoke layer starting to encroach, and it's embedded in this midday, late afternoon wind, and now we're going to watch it spill across the mountain range and very slowly. Here, maybe I'll advance it a little bit in the interest of time. You can watch it start running down the mountain slopes. Oh, I can't find my little thing. We'll just have to let it go on its own, I guess. Very slowly, it's going to kind of start spilling down the slopes into the Tahoe Basin, And this is actually behaving like a really interesting type of flow that we get in the atmosphere, which we call density currents, which is kind of cold air that spreads out along the surface. And one of the really counterintuitive things with these smoke layers is actually a lot colder inside the smoke layer than it is outside of the smoke layer, because it's blocking a lot of the sunlight. And so that solar radiation isn't getting absorbed at the surface. And so here we go. Now we can see it spilling into the basin. And eventually this will go on and fill the entire basin and keep running over into Nevada. And unfortunately, what's in here is lots and lots of very, very small particulates, which are not particularly healthy to breathe. And so it's something that we call PM 2.5, or particulate matter less than 2.5 microns, which is about 1/10 the diameter of a human hair. And that's problematic because these really small things evade most of our natural filtration systems. Mucous membranes and hairs in our nose and stuff like that, and they can actually diffuse into your bloodstream. And so the health impacts of breathing a lot of smoke like this are really not particularly good, especially for chronic exposures. And we see things like increased risk of stroke. Actually, counterintuitively, one of the biggest impacts is not necessarily respiratory impacts, but cardiovascular system impacts, because it actually gets into your bloodstream and affects your veins and arteries and things like that. So there we go. Now we have a bleak view of the lake after the Washoe Zephyr has brought all this smoke in. So you kind of put these two things together, lots and lots of fire and some peculiarities of the local wind systems that we get here, and we really have a recipe for a lot of smoke in the Tahoe Basin. We have some new tools for looking at this that have just come online in the last few years. This is just a little animation. Let's see if I can get this one to run here. There we go. Of a new model forecast that's produced actually every hour and run out for about 18 hours, and some runs out to 36 hours. Let's see if I can play that again. And what this is a weather prediction model coupled to a fire model that then puts the smoke into the atmosphere and lets it get blown around by the wind. And it lets us develop better and better forecasts for where this smoke is going to end up on a daily basis. So I think this was from late this summer. This was probably, I actually can't remember the name of this fire here, and this is a little north of where the Carr Fire was, but this was after the peak of our fire season. But you can see all these fires burning through the Northwest and the distribution of smoke that we get from these. And I've added a link right here at the bottom so you can actually go look at these forecasts in real time next summer when we get back into fire season, if you're interested in figuring out which day you should go for that century ride and which day you shouldn't. That's a great resource. So these models are great, but they come with a lot of caveats. There's a lot of assumptions that go into this. And there's a lot of unknowns, and that's really what my research focuses on, is trying to understand some of the processes going on behind the scenes that we then have to represent in these models. And this is something that we call fire-atmosphere interactions. So that's actually what I'm going to spend the bulk of the time talking about today. And I spend most of my days talking to physicists about these things, so I'll try to keep this real, but feel free to interject with questions if I'm saying something really abstract that makes no sense. So, all right, so I just want to introduce kind of two terms here. One is fire weather. This is a term that maybe some of us have heard before. We think about things like red flag warnings. And I would say mostly what this boils down to is hot, dry, and windy, which isn't exactly rocket science, right? Most of the summer is hot and dry, and then we get a handful of days that are windy, and those are the particularly problematic days. And so that's a weather forecasting challenge. We can look at our prediction models and figure out when it's going to be hot, dry, and windy, and hope that people don't start fires on those days. Unfortunately, people go and start fires on those days for any of a gazillion means. About 80 to 85% of fires in California are human started, so not lightning and natural causes. So in other words, they're avoidable in theory. But the more complicated thing that goes on and that we need to understand in these models is this idea of fire-atmosphere interactions. And this is basically how fires produce their own weather. So fires put a lot of heat into the atmosphere, and that heat drives really strong updrafts. And just like having smoke go out your chimney, the air has to be replaced from somewhere. So it has to get drawn in from the sides in the form of inflows coming into these wildfire plumes. And it then goes up, and then it has to spread out at some level. And it can even do things like form its own weather systems in terms of clouds forming at the top of these wildfire plumes. And so collectively, these processes, this kind of set of interactions in here, actually has a lot to do with the way a fire behaves. Is it going to get really big? Is it going to move really fast? Is it going to throw embers out in front of itself and propagate across the landscape in interesting ways? So that's kind of this picture. Understanding all the pieces of this is really what I focus on. And why do we care about this? Well, I mean, we all live in a very fire-prone environment here, but we're also coming off the backs of what are two of the most costly and deadliest wildfire seasons in California history. 2017, actually today, is the anniversary of the North Bay fires, where we had kind of unprecedented loss of civilian life in California, especially in Santa Rosa, pictured here. And so really there's a kind of pressing need to be able to understand how these fires behave so that we can predict them and hopefully get out in front of them in the future, although that's kind of a long ways off. Solving the smoke problem that's a long ways off, yeah. All right, so how do we go about understanding this stuff and improving it? Well, we do a field campaign where we go out and we collect observations. And so this was something that we called RADFire, which stands for Rapid Deployments to Wildfires. And the goal of that project was to advance our understanding of these fire-atmosphere interactions, and especially the big wildfire plumes that develop. And the methods that we used for this were to use some rapidly deployable instrumentation to get fire line qualified. So we all took wildfire training courses to go out so that we could get proper and safe access to these fires, and basically go out and do fire chasing. So instead of doing tornado chasing like people do in the high plains, we go out and we chase fires around California. And we bring a whole suite of atmospheric observing tools with us. So during the summers of 2014 to 2016, we made it out to about 22 major fires around California. So we were pretty busy for those couple of years. You can see a map here of the different fires that we went around and sampled. And then here is a picture of kind of our measurement strategy. You leave the doors open so you can get in real quick and get out of there. The main instrumentation platform is this kind of storm chasing truck that we use. And this has some kind of sophisticated instruments on here. So it's an F-250 truck. And the key instrument on the back here is something called a scanning Doppler Lidar. So Lidars have become very popular because they're the kind of central technology used in a lot of self-driving cars now. They're really good at detecting distances between things. You can also use them in the atmosphere in the same way we use like a weather radar to look at the structure of, in this case, smoke, and also the strength of the winds in those systems. So this thing has a laser that spins around and shoots out into the atmosphere. It goes about 10 kilometers away, and so it can kind of paint a picture of the wind flow around these wildfires, so we get a sense for how they're modifying their environment. There's some other stuff on here. We have weather balloons and all sorts of other instruments, and also today I'll be talking about weather radars. That's literally the same tool that we use to look at precipitation systems and how we use those to look at wildfires. This is just an example of what the LiDAR can show us. It's kind of like taking a CAT scan or an MRI of the plume coming off of a wildfire. So here's a case where I have the truck parked over here, and there's a fire up here on the slope, and it's putting this plume up into the atmosphere, and you can kind of watch how this evolves in time. And that's interesting to us because historically we haven't been able to do things like that. We used to do these things just in a laboratory experiment, try to make a scale model of this and drop some fluid into a tank, and really has nothing to do with the way wildfires actually work. So that's just kind of exciting application of this technology to the real world. Oops, let's go back here. All right, so go back a little further. All right, so the first manifestation of what I would call extreme wildfire behavior that I want to talk about that we've been able to observe is the development of really strong or tornado-like rotation in these wildfire plumes, which is really scary if you're a firefighter or if this is impacting a place where houses are. So we might go from a situation like, let's see if this will work, maybe not. Oh, there we go. It's starting where we have an initial plume that's starting. This is a fire that's starting more or less right in front of us, and it's drawing air in from all sides, just sucking air into the base and pumping it up through effectively a chimney. But if we let that process go for a while longer and look at it later, this thing will start developing really strong rotation in it, much like a tornado does. And so we go from a situation where we have flows just coming in from the side to a situation where we have very strong and rotating flows, which can be really hazardous for firefighters and really significantly impact the way these fires move. And so we're able to make scans with this Lidar right through the base of this rotating column of rising smoke. And I don't know if anybody's ever watched like tornado chase videos where people go out with radars and look through the base of these plumes, but what this image up here is showing us is the wind field associated with this. So by scanning my laser right through here, I can see the structure of the flow associated with this. And I can see this really strong inflow that's wrapping around this side, and another inflow in the clear air that's coming around this side, and forming this very tight rotation right in here. And in this particular case, that rotation is literally as strong as it is in low-grade tornadoes. So that was kind of interesting to us to be able to see that. Another thing that was interesting is asking the question, how could this thing get stronger in time? And when we went back and looked at all of the data that we collected, what we saw is that it's not really apparent in the video, but there are actually two different, what we call vortices next to one another that merge over time. So I'm highlighting those on here. So here's vortex A and here's vortex B. And if we watch in time, those two vortices come together and then form a bigger and stronger rotating convective column. And so what this has allowed us to do is understand one of the principal ways that these things get stronger in time. They feed themselves with these little vortices that come in from the side and then get stronger and stronger. So just a kind of cartoon schematic of what I'm talking about here, we start out with a plume and it's really hot, so it has a lot of rising air, drawing air in from the side. Over time, it develops rotation. I'll talk in the next little bit about how it develops rotation. But one of the ways that it strengthens is it forms another little vortex next to it, which orbits the bigger one and then merges into the middle. And I do have a photograph right when this merger was happening, and you can actually see these two different rotating columns intertwining with one another, like a helical shape in the way this plume is developing. And you let this process go on longer and longer, and eventually you get stronger and stronger rotation that can reach tornado strengths with time. Okay, so that's kind of what I would say like a run-of-the-mill tornado-like circulation that develops from a wildfire, but unfortunately, these things can get much, much stronger. So I don't know if anybody followed the news with this Carr Fire in Redding, California, but here's a video of a rotating column of flaming gases coming off of the Carr Fire, and this is in real time, and you can see the extreme strength of this rotation in here, and unfortunately the tremendous devastation that's going on at the base of this thing. One of the things that happens when the column starts rotating is it actually gets hotter, and it gets hotter because it gets less good at mixing cold air into that column. It kind of isolates itself, again, like a chimney. And so the fire actually gets hotter and more intense in the middle of these big wildfire vortices. I think there's an even more sensational video of this from this fire truck dash cam, and you'll see them turn the corner here in a moment, and look up the street to this massive rotating column of flaming gases and smoke. And so, whereas the first example that I was showing you just kind of was towing the line with tornado strength, this particular fire vortex had winds that did damage like this. So both within the combustion zone and outside of the combustion zone, there's extreme damage. So this is a house outside of the combustion zone where the roof has been stripped off by the winds induced by this vortex. Here we have a steel pipe wrapped around a tree. This was a high tension power line and a number of vehicles that were destroyed by this. And so you get the sense of the extreme devastation that something like this can bring. These are the sorts of things that our models don't produce. These are things that aren't in our models of the way a wildfire behaves. And so the National Weather Service went out and they did a damage survey for this in the same way they do damage surveys for tornadoes. And they estimated that the wind speeds in the base of this column were about 143 miles per hour. So really extreme winds here. And that says nothing about the intense combustion, which was probably about 2,600 degrees. So you can imagine what would happen to your car. It literally melts in conditions like that. So I've been working on a project to actually try to understand this particular vortex and how it formed. And like many of these things here in the West Coast, they're embedded in kind of a climate background. So it's always important to zoom out a little bit and think about what the context is that's allowing fires to get so hot and so intense. And so these two maps, which were produced by a colleague of mine, showed two things about July. So this fire occurred on the 26th of July, 2018. This is showing the departure from normal in the nighttime temperatures that we had during the month of July. And the nighttime temperatures were running 3 to 4 degrees above normal, 3 to 4 degrees Celsius above normal for the entire month of July. That's a big departure from normal. And that matters because at night is when relative humidity usually rebounds. You know, you wake up in the morning, you see some fog down by the airport, right? It cools off at night, we get some humidity in the air. That humidity gets pulled into the fuels, moistens up the fuels, suppresses the fire activity. If it's really hot at night, that doesn't happen. And in fact, if we look then at something that we call the fuel moisture, so this is how much water content is in the fuel, how combustible the fuel is, there's a bullseye right over the Redding area, right where this fire occurred. And so it's occurring in a region that has a big departure from normal in terms of the combustibility of the fuels. So that just kind of sets the stage for something like this, where we have the ability to heat up our fuels and cause a really intense fire really quickly. The next thing that we have to think about is how the weather on that day can impact a wildfire like this. And so we're looking at a map here showing the wind field and the way you interpret this figure. So Redding is right here and the fire perimeter is here. And so along the axis of the Central Valley, we have a southerly wind coming up the valley. But if we look up here over the fire region, we actually have a northwesterly wind that's coming in the late afternoon. And right between those, we have something that we call a wind shift line, which is marked by these shaded colors right here, which shows us the amount of local spin there is in the atmosphere. A fancy term for that is vorticity, but it's basically showing how much ambient rotation there just happens to be in the atmosphere at that point in time. And so we have this strip of air right along here where there's this boundary between two opposing wind flows, and those are kind of setting the stage for there to be a source of rotation for a storm system like this. Interestingly, the setup that allows this is very similar to the Washoe Zephyr. It gets really, really hot here in the northern Central Valley. It was 113 degrees Fahrenheit on the day of this fire, which draws air in effectively from all sides in its own right, and that's why we're getting this distribution of winds. And so this is important because it's setting the stage. So we have explosive fuels, and then we have, on top of it, some local spin in the atmosphere that just happens to be there because of the weather flow, or the wind flow on that day. So what we can then do is use weather radars, the same tools that we use to look at rainstorms in California, to look at the structure of this tornado strength vortex that formed. And let's see if this works here. There we go. So we're able to reconstruct the three-dimensional structure of the fire on that day in this massive plume that is coming off of the fire. So what we're looking at is Redding, California is right here, and here's the fire perimeter. And this is the big plume of smoke that is coming off of the fire and extending up to about 12 kilometers, which is about 39,000 feet in the atmosphere. So this is the level that you're flying in jet aircraft going across the country. And the vortex that we saw in the video is identified in the black line here, and it extends from the surface up to at least 15,000 feet. So not only is there really strong rotation down at the surface of the Earth, but through this huge column way up into the atmosphere, which is one of the reasons this is able to get so strong on this day. This is a really complicated figure. Let me see if we can work through this really quickly here. What we're looking at is slices through the wildfire at a number of different levels. So this is at the lowest elevation, and then time is increasing in these successive panels off to the right. And then this is at a higher elevation, higher still, and at the highest elevation. So the radar beam is slicing through this wildfire plume at different heights. And what this is showing me is that local spin in the atmosphere. The difference between these blue and red colors, and this red line is the fire perimeter, is showing that right over the fire perimeter, even before this tornado forms, there is a lot of opposing flows in the atmosphere. And so you could think of this as like the median in a highway where you have 70-mile-an-hour traffic going that way and 70-mile-an-hour traffic going that way, and it's separated by just a little bit of a distance in there. And in the lead up to the formation of the tornado, which happens about here, that flow gets stronger and stronger, the opposing flow. So there's kind of this concentration of this spin in the atmosphere. And eventually it gets so concentrated that it forms this very compact couplet, which is this really close together red and blue dots right here show really strong shears in the atmosphere, flow going back and forth like that. Over time that gets stronger, and then it extends to higher and higher altitudes with time. So it starts out near the surface and it gets drawn up into the atmosphere with time. What this figure here then is showing is the strength of that circulation. How strong is the rotation of the winds in here? And what I want to point out in here is that what we see is a curve that we would describe an exponential increase with time. Whenever you see exponential increases with time, that should send off kind of alarm bells. This is like runaway, well, that's good in your bank account, actually, when that happens. That's probably the most familiar thing. But in nature, when things like this start happening, we're usually talking about rapid intensification of a system. So we go from just some winds that are going like this past one another to very, very rapidly these 143-mile-an-hour winds. So how is that happening? Well, it's happening because when you stretch the atmosphere out into the vertical, you concentrate that local sense of spin. This is kind of like a figure skater analogy. So in the period where, what this is showing is the radar data showing the height of the plume, how it's changing with time. So initially it's around 6,000 meters or 15,000 feet. And just about 15 minutes later or 30 minutes later, it's around 39,000 feet. So we see this rapid increase in the depth of this wildfire plume. And so you can think about this like a column of the atmosphere that's getting tugged on really strongly and stretched out into the vertical. And when that happens, we take whatever rotation was there initially, and just like the figure skater, which I'll show in a moment, pull your arms into the side and you start spinning faster and faster. And then just the opposite happens during the decay cycle of this. The plume rapidly collapses, the fire shuts off for a period of time, and we get a huge amount of compression of the column, and the vortex dissipates almost as quickly as it formed. So like I mentioned, this is analogous to the idea of a figure skater that starts rotating with their arms out wide, and as they draw their arms in, that is the same in the atmosphere fluid dynamically. That's the exact same as stretching a column really strongly in the vertical, and we concentrate that rotation with time. And so we have all the ingredients that we need. We have some background spin, and then the fire is providing this huge stretch to the atmosphere to form this vortex. Why does the plume get so big so quickly? it's not just about the fire is the really interesting thing here. We get lots of fires in California. Most of them don't produce tornadoes. Most of them have really hot flames. Flames are hot. They're always hot. What's different about this case? Well, what's different about this case is if we look at a satellite view of this plume coming off of the fire, so this is one of our newer satellites, we can look at this kind of protrusion coming up from the smoke layer over Redding. And what's happening here is that the wildfire is actually triggering its own cloud. And when it triggers a cloud, it actually releases something that we call moist instability, which is the same way a thunderstorm forms in the atmosphere. So with time, that cloud gets bigger, and then much bigger, and then suddenly we are literally forming a thunderstorm off the top of the wildfire. And this process is what allows it to go very quickly from something that's 6 kilometers tall, based on just the heat of the fire, to 12 kilometers or 39,000 feet tall. And so these are a type of cloud that we call pyrocumulonimbus clouds, or pyro-CB for short. And they're rather stunning to look at. They look like this. How many people have seen one of these before? Okay, a handful of you. We live in a pretty good location to see these. The King Fire produced some good ones, or bad ones, depending on your perspective. I always have to be careful with my terminology. But so what we can see is somewhere up in this plume, we hit what's called the condensation level. It's really hot down here, but by the time you get up here, this thing actually cools off really, really rapidly and gets so cold that it forces the water out of the air to form a cloud. And in fact, it gets cold enough that it turns to ice. The top of this cloud on this day was about negative 52 degrees Fahrenheit. So you go from a 1,600 degree fire to negative 52 degrees at the top of this plume. Pretty impressive. So the growth of this pyrocumulonimbus cloud is really the responsible mechanism for generating this, this pyro-tornado, if you will. We can also track the intensity of the fire as it changes from satellite as well. So what these kind of red and yellow pixels show is looking down from space at the fire, going from the period where there's no pyrocumulonimbus cloud to the period where there is a pyrocumulonimbus cloud. And you'll note this bright yellow dot that shows up right in here. This is the most intense pixel of the fire. This is where it's the hottest. And if it's probably a little bit hard to see, there's a little white circle that I have on here. That's the location of the vortex at the surface, where unfortunately all those houses are getting consumed. So this drives up the fire intensity quite significantly. All right, so let's look at a quick cartoon image of how this happens. We start out with a fire, and that fire is embedded in a location that happens to just have some background differences in the wind. And that's an important ingredient here that separates this from a lot of fires, just essentially happenstance that it exists in this location. As the fire intensifies, it provides a stretching mechanism, and it makes this background wind shear stronger with time. But that alone would not form a tornado-strength vortex. Instead, it's when the cloud or when the plume gets deep enough that it triggers the development of this cloud. The height of the plume goes nuts, for lack of a better way to put it, and collapses the circulation in that exponential growth cycle into a tornado-strength vortex. And for those of you that have watched the movie Twister, this then does things like that to cows. Yeah?
Can you explain again why this radical radical temperature low on the top of the cloud?
Sure. Yeah, when air rises in the atmosphere, it encounters lower and lower pressure. Gravity holds most of the air close to the surface of the Earth. And so you can see this if you take a bag of chips from Reno and drive up, right? It distends the bag. And there's a law in physics called the ideal gas law that says that when that happens, the temperature also has to go down. And so when you lift something from the surface up to 49,000 feet, the amount of expansion that it goes through necessitates a certain amount of cooling. And it cools at a very specific rate when there's no water in it, and then actually at a lesser rate when there is water in it. But that's how you can go very rapidly from something that's very hot to something that's very cold. There's more to it than that. It also mixes a lot of air from its environment into it. And so it's kind of all these bubbles on the side are folding air from the environment into that and diluting it with time. But yeah, it's pretty wild to think about a fire. It's literally fire to ice, you know, from the surface up to the top of this cloud. Yeah, great question. Yeah.
Does that?
Oh.
Does the line there where you're saying it's clouds, did those clouds contain smoke all the way to the top, or are those a different thing than the smoke that you're seeing lower?
That is an excellent question. We don't entirely know the answer to that. Most of the time they are going to contain smoke, and that smoke is actually going to change the characteristics of the cloud. The smoke actually acts as what we call a condensation nuclei around which the water condenses. It actually forms droplets around the smoke particles. And then when the water evaporates, eventually it leaves the smoke behind. And so this is actually one way that we can get smoke all the way into what's called the stratosphere, which can then circle all the way around the Earth over the matter of a few weeks. So typically it contains smoke, but there are some circumstances where a cloud will form above it that isn't really connected to the flow of air all the way up through there. Yeah, good question.
Hypothetically, what would be the highest speed that one of these could accumulate?
Rotational speed or updraft speed, I guess. Would be the question.
Rotational speed.
We're probably looking at it. To be perfectly honest with you, it's probably right around here, right around 150 miles an hour. Big tornadoes get stronger than that, but they form in environments that have much more background wind shear. They have more energy to work with, and they release more moisture into the atmosphere. So for a fire-induced tornado, I've got to say this is probably about the upper limit that you would expect. And this is actually only one of 2 fire tornadoes of this magnitude that have ever been documented. So yeah, we don't have a lot to work with, I guess, for data.
So, like, how much of the tornado part of the fire tornado is actual fire, and how much of it is smoke?
Yeah, the fire actually fades out pretty quickly with height. It's probably only the lowest few hundred meters, so maybe 300, 400, 500 feet above the ground. And then above that, it's just going to be smoke. But that's already getting flames 300, 400, 500 feet above the ground is a lot higher than you would get just from. Excellent questions. All right, so just a quick summary of this was that slide that I showed. We have this shear zone in place. It's kind of important because maybe there's some potential for early warning for things like this. If meteorologists are paying really careful attention to a given fire and can recognize some of these conditions, you might be able to put out that warning a little bit ahead of time. The vortex formed with the growth of this cloud. Without that, we probably wouldn't have gotten that. And there's some kind of debate in our community right now about whether this is a tornado or a fire tornado or what exactly to call something like this. Frankly, I don't really care what we call it. It is what it is. And I don't think if you're in the way of it, you care either. It's a intensely rotating column of very, very hot air, and you really don't want to be there. So hopefully we won't get things like this here, but this is a manifestation of extreme fire behavior, which you get when you have extreme fuel conditions, which unfortunately we're expecting more of in the future because it's going to be hotter. All right, so the last topic, and I'll move through this pretty quickly, we just talked about how strong rotational winds can get. Those rotational winds have to be linked to a really strong updraft somewhere in here. So the other question is, how strong can these updrafts get? And we had an opportunity to look at this in a fire, not here in California, but out in Idaho, called the Pioneer Fire back in 2016. And instead of using ground-based instruments, we had an aircraft flying around this. I was not on the aircraft for this mission. So here's the fire. You can actually see some of these clouds forming off the top of the fire right here, these pyrocumulonimbus clouds. They're going way up, actually out of view here. But so we flew this aircraft equipped with a radar that points down out of the belly of the aircraft and can look down into the wildfire. And so we can ask questions, how strong are the updrafts in these massive plumes in order to get the air up that high? And we care about that for a number of reasons, including the development of things like pyro-tornadoes, but also smoke dispersion. When you put smoke this high into the atmosphere, it goes a long way. It affects people on the East Coast, it affects people in Europe. It can actually cool the Earth a little bit, which is maybe the one plus side of it. To date, we've never been able to look inside of one of these before and really see how strong those updrafts are. So this was an exciting opportunity for us. So this fire went through massive expansion on the day of observations. It burned through about 30,000 acres. This is the expanding flank of the fire right here in the middle of nowhere, Idaho, which is most of Idaho. And then that's it at the end of the day, and that's about 30,000 acres of growth, which is big for a fire going through mature timber. This shows the top heights of the plume, how high the plume got. So just like the Carr Fire, it's up to about 12 kilometers, or about 39 or 40,000 feet that this plume went up on that day. And here is the ill-advised flight track on that day. The first few flights actually cut right across this monster before they figured out that was a really bad idea. And then they spent the rest of the day playing around on the edge of it. So what does this look like? Well, the aircraft's flying along on this dotted line up here, and it's looking down, and these red and blue colors show the updrafts and downdrafts. Blue is going down, red is going up. So the aircraft's flying at about 5 kilometers above the surface, about 16,000 feet, something like that. And it comes along and it does something like that. Right at this blue dot, it runs into an extreme updraft of 36 meters per second, which is 90-something miles an hour, I think. So that's not the sort of thing that you're supposed to fly through. I like to call this the first and last aircraft penetration of a pyro-CB, because the program sponsor has told us that we are not allowed to do this ever again, and I agree with them. I think that would be a good idea. This figure just shows the huge spike in the updraft up to 36 meters per second. Sorry, I do everything in SI units, just the way we roll. It's also really, it's warmer in there than the environment, but it's not a lot warmer. It's only 4 degrees warmer than its environment. So back to that question of how quickly this thing cools off, it was 1,600 degrees warmer than its environment. Now it's only 4 degrees warmer than its environment, and it will go up until it's colder than its environment. Here's some more sensational views. After they decided to not do that again, they flew at a higher altitude above the top of this thing. So again, the red colors indicate up, blue indicates down, and these are 3 successive overpasses of this developing pyrocumulonimbus cloud. And in all of these, what we see is a strong central updraft flanked by very strong downdrafts on the side. And so this is actually mechanically generated. As the air forces itself up, it has to force some air back down in order to conserve mass. Yeah. This is not actually a Lidar, it's a radar, so it's using a much longer wavelength than Lidar wavelengths, and it lets us actually see into the plume a little better. The Lidar wouldn't be able to see this as well. It's a millimeter wavelength radar, which is the same thing they use in aircraft screening, TSA stuff.
I was wondering if there had been any use of unmanned drones to document this type of stuff?
There is, but only on small prescribed fires. The mission on these big fires is always protect life and property. And as soon as there's fire suppression aircraft in the air, they don't want drones anywhere near it. And so it's in some ways an impediment to the research, but you can certainly understand if you're a helicopter pilot not wanting in order to do this, even with an aircraft, you have to get special clearance and stay above something called the temporary flight restrictions, the TFR, to get above the altitude where any of the fire suppression aircraft are flying. So we have some experiments planned in the future with big prescribed burns with UAVs, but for wildfires, it's pretty much no-go. Good question. But the really radical thing in here is the central updraft here. The aircraft hit 36 meters per second for an updraft. when we flew over it at a higher altitude and looked down, the updraft was 58 meters per second or 130 miles an hour. So if you flew a commercial aircraft through one of these things, this would be trouble. And so this is a serious risk for aviation. But this also explains how these things are able to get to 12,000 meters or 39,000 feet is with these intense updrafts. And we see the same general structure every time we fly over it, big central updraft, flanking downdrafts. The downdrafts on the edges can be as strong as 30 meters per second or upwards almost to 100 miles an hour. So again, flying through it, you get the extreme down, extreme up, extreme down, really bad recipe. So yeah, we've been able, just in the past 2 years now, to kind of answer a few key questions. How strong are those updrafts? How vigorous of a rotation can you develop in these? But there's still a whole lot that we need to understand about wildfires. And so we're developing our next phase of observational campaigns that are going to include lots of really expensive tools, dangerously close to wildfires, but not flying through it again. So in the future, we hope to use this same aircraft to fly above it, and then scanning radar trucks at the surface. We just got funding for a new radar that we're going to put on the back of this truck, which is good at getting close to these. And we're also going to have infrared sensing of the fire development, so we'll be able to link all of these things together. And so I have no idea what time it is. I've probably run too long, but I'm gonna leave it there and happy to take questions.
Two questions. So one question, you showed that one picture of, or the one video of the fire truck with the dash cam going around the corner, and seeing that striking plume, and I'm like, let's get the hell out of here. And so, what is that what the firefighters are doing?
Yeah, unfortunately, a firefighter was killed during that event, very near there, trying to evacuate people from their homes at that time. But yeah, they cease operations. I mean, there's a point at which you just stop direct engagement with the fire and go into evacuation mode or safety. You know, the training is you go to the safety zone. And so, yeah, there's really no way to directly attack something like that.
And then, so the second question, so here we live in a different geography, and we have the Zephyr winds that come through here. I want to call them Tahoe winds, but, and they're pretty consistent in their direction because of they live off of the land. Mm-hmm. So how does that affect the fire behavior?
Yeah. They are very consistent in their direction in the late afternoon, and so they can drive really rapid fire spread in that downwind direction and give you a wind-driven fire, which can chew through a lot of terrain in a short period of time. So they're one of the kind of lookout situations for around here is days with strong washoe zephyrs or just strong southwesterly winds that would drive a fire. You know, if you have light winds, your fire is going to tend to run up slope. But if you have a background wind compelling the fire to go in a direction, it's going to listen and it's going to go with it. So, including in the downhill direction, and that's one of the things that makes winds like that dangerous. Is typically, you know, we think about fire running up to the ridgeline, but when we get something like the Washoe Zephyr or the winds that drove the Tubbs fire into Santa Rosa, those are a form of downslope winds, which will counterintuitively drive the fire downhill. And that, unfortunately, tends to be when we get, you know, impacts on homes more than anything. Yeah.
So I have a question with regards to how fast these plumes move. With a true tornado, you know, it can move very slowly. I've spent a lot of time in Oklahoma, and or very quickly. And I was just wondering, you know, do you have data on, you know, how much time do you have to get out away from the flume?
Yeah, it really depends. Interestingly, that big vortex barely moved. It only moved about 2/3 of a mile in about 30 minutes, and it was fixed right to the fire perimeter, which is very different than the way a true tornado is going to move, because it's being driven by strong background winds. So yeah, if you're locally in the way, I mean, it's extremely hazardous, but it's not going to race up to you in that sense. Whereas these other cases where we have are called wind-driven fires, as opposed to something like that, which is what we call a plume-dominated fire, then the fire can move extremely rapidly. And again, going back to today, the anniversary of the North Bay fires, that's what we saw there. Extremely rapid wind-driven fire spread. And you also get spotting of those fires in particular, where they're throwing embers out in front of where they are. And so you think the fire perimeter is over here, but you have new fires starting behind you. And so you get, it's not just driven by the wind, but it's hopscotching through the landscape and then burning all together, which makes it even more dangerous. Yeah. Yeah. Yeah, that's a really good question. Yeah. So I think the question was basically, how does kind of fundamental research like this translate into improvements in prediction? And what we do with models is we try to represent these physical processes that occur in some sort of simplified framework. You can never represent the full complexity of the world in the model. And one of the fundamental tests that you then want to do with the model is compare it to observational data. So my research team, often what we're doing is producing data sets that are used to validate simulations. And then you diagnose what the simulation did wrong. The simulation didn't form a fire tornado. Okay, why didn't it form a fire tornado? What physics do we need to add to the model that aren't in there to get it to produce something that looks like reality? And so, yeah, with a lot of the field experiments, you're producing data sets to validate numerical models, which can then ultimately, hopefully, predict this. And that's the same thing that we do with weather prediction models. We have a longer way to go to getting the coupled fire and atmosphere models to the point that we're going to be able to offer a good forecast for where the fire is going to be in 12 hours. But people are starting to run those models. You know, in 15 years, there will be forecasts in the same way that it's going to rain at 8 p.m., the fire is going to be here at 8 p.m. That's in the pipeline, but it has a ways to go. Yeah. Great.
Thank you. So I'm not looking forward to that forecast. I should use the microphone too. So as I just said, I'm not looking forward to ever receiving that forecast, but I'd rather receive it than being surprised. So it's, I think, a very valuable work. Thank you so much. And it's a reminder of life can be dangerous, and we all have to pull together to get ahead of the fire. So thank you. Fascinating talk.